In the next reaction, a phosphate is transferred from 1,3-diphosphoglyceric acid to ADP to make ATP by substrate level phosphorylation, leaving behind 3-phosphoglyceric acid. Now remember again, this reaction, like all of those in the second stage of glycolysis, is occurring twice per starting molecule of glucose. The reaction is catalyzed by phosphoglycerate kinase. It's also exergonic with a standard free energy change at delta G0 of minus 4.5 kilocalories per mole. In this reaction, the endergonic synthesis of ATP by substrate level phosphorylation is coupled to a much more exergonic reaction, the hydrolysis of 1,3-diphosphoglyceric acid. This reaction is reversible, the arrows can tell you that, and in active cells it's very rapid, which, by the way, is why we saw earlier that the concentration of G3P in cells is usually very low. Now, why do you think we would refer to 1,3-diphosphoglyceric acid as having a very high energy phosphate linkage? Because the hydrolysis of a phosphate from 1,3-diphosphoglyceric acid is very exergonic. To demonstrate this for yourself, write the reaction as the sum of an ATP dehydration synthesis reaction plus a 1,3-diphosphoglyceric acid hydrolysis reaction. You can refer to some of the examples of this sort of thing that I presented earlier to get you started. The next two reactions are each modestly endergonic and freely reversible. First, the phosphate group on the 3-phosphoglyceric acid, or 3PG, is shifted to the number 2 carbon by a mutase in a reversible endergonic reaction. Then 2PG is converted to phosphoenol pyruvate, or PEP, in another reversible endergonic reaction. Like 1,3-diphosphoglycerate, phosphoenol pyruvate, PEP, is also a very high energy phosphate compound. In this quite exergonic reaction, delta G0 equals minus 7.2 kilocalories per mole, the hydrolysis of phosphoenol pyruvate is coupled to the synthesis of another molecule of ATP. The enzyme catalyzing this reaction is pyruvate kinase. In energetic terms, the large amount of free energy released by the hydrolysis of the phosphoenol linkage in PEP is what drives the endergonic ATP synthesis. Again, demonstrate this to yourself by writing the overall reaction as the sum of two separate reactions. Pyruvate kinase catalyzes a biologically irreversible reaction, and the enzyme is allosterically regulated. The enzyme is inhibited by ATP, citric acid or citrate, and long-chain fatty acids of the sort you would find after they were immediately hydrolyzed from the glycerol backbone. And the enzyme is stimulated by fructose 1,6-diphosphate and by phosphoenol pyruvate itself. What is the logic for how each of the allosteric effectors I just told you about regulates pyruvate kinase? Here's a balance sheet for glycolysis of a mole of glucose to 2 moles of pyruvate. We have consumed 2 molecules of ATP, but we synthesized 4. That's a net of 2 ATPs produced. The 2 ATPs account for a capture of approximately 15 kilocalories of the free energy once in glucose. We end up with 2 molecules of pyruvate, as well as 2 molecules of NADH, along with 2 protons. Well, where did the protons come from? In glyceraldehyde 3-phosphate oxidation, a whole hydrogen molecule is removed from G3P, but NAD+ grabs only the hydride ion. That leaves a proton behind in solution, and that's where the proton comes from. The standard free energy change for the whole of glycolysis through pyruvate can be summed up. Just add all the free energy changes for the reactions as I've shown them to you, and it comes to minus 44 kilocalories per mole of glucose. Now that's 44 kilocalories out of a potential of 686 kilocalories for the whole respiratory pathway from glucose and oxygen to water and CO2. So at this point, where is the free energy that was once in a molecule of glucose or in a mole of glucose? Well, a small amount is in ATP, so most of the rest must still be in the 2 pyruvates and in the 2 NADH molecules. Let's take a moment to look at some of the different phosphate linkages, some of which release a lot of free energy when hydrolyzed, and some of which do not. First off, the hydrolysis of an enol phosphate linkage, such as in phosphoenol pyruvate, and the phosphoanhydride linkage in 1,3-diphosphoglycerate are both highly exergonic. Hydrolysis of the phosphate linkage in creatine phosphate shown here is also very exergonic. You can look up the role of creatine phosphate in providing energy to make ATP for muscle contraction on your own. Hydrolysis of the ATP phosphoanhydride linkage is also exergonic, but not as much as the linkages in PEP or 1,3-dipG. So calling ATP a high-energy intermediate was in fact a good call. Lastly, there are many phosphate ester-linked molecules. We've seen some of them, like glucose 6-phosphate shown here, or AMP, adenosine monophosphate, whose hydrolysis, while exergonic, will not release enough free energy to be coupled to ATP synthesis. Glycolysis from glucose to 2-pyruvates is sometimes called incomplete glycolysis. Complete glycolysis is a fermentation, which occurs under anaerobic conditions.